Magnets are small objects that are capable of attracting and being attracted to other objects. Magnets are typically made from ferromagnetic substances such as steel. Substances which are attracted are also typically made from ferromagnetic substances. Magnets have two regions created in them known as poles, and one pole may not exist without the other. The Earth acts like a giant magnet, and its magnetic poles make magnetic compass direction finders possible.
The north-seeking pole of a magnet, suspended from a piece of thread, will swing to point north. A cradle can be made from a piece of wire to hold a bar magnet. When an ordinary piece of steel is placed in the cradle, no change in its orientation will be observed. A horseshoe magnet's north-seeking pole will also point north. Generally, once a magnet starts to move, it builds up momentum which will lead to it swinging past the north direction, and will slow down as the effect of the Earth's magnetic field continues to work on it. This will lead to a harmonic swinging motion which will dampen with time, providing that it is not affected by motions of air. Presenting the pole of another magnet to the suspended magnet will exclusively attract or repulse the particular pole that is nearest to the presented pole. It is found that a north-seeking pole will repel the suspended magnet's north-seeking pole and will attract the suspended magnet's south-seeking pole. A presented south-seeking pole will repel the suspended magnet's south-seeking pole and attract the suspended magnet's north-seeking pole. Another example of the Earth's magnetic field attracting a magnet may be observed by placing a magnet on a floating flat cork. The water should be filled to the top of the container, otherwise the cork will move towards the side of the container and stay there. The magnet and cork again repeat a harmonic motion until they settle down. Again, an unmagnetized piece of steel will make no motion. The attraction and repulsion of magnetic poles may be further demonstrated by the use of two convex magnifying glass lenses arranged to pivot one on top of the other. A magnet is placed on one of the lenses and held in place with some blue tack in order to prevent independent motion. A second bar magnet is held in place underneath a Petri dish. It is worth noting that by itself the contraption does not have enough impetus to align with the magnetic field of the Earth. Magnetic compasses are examples of small needle-shaped magnets enclosed in protective cases to allow free pivoting movement. Two compasses will, however, affect each other. As they move closer to each other, they align to accommodate the magnetic field of the other compass, rather than the weaker magnetic field of the Earth. A steel nail brought close to the compass will also affect the direction the compass points, as magnets are attracted to ferrous materials. A steel post in the ground will eventually acquire a magnetic field after being in that position in the Earth's magnetic field for a while. This is demonstrated by bringing a compass near the bottom of the post and moving it upwards. There is a point in the escalation of the compass at which the compass will swing around such that the other pole of the needle is attracted to the post. It is possible to magnetize pieces of steel like hacksaw blades. The process is to use a strong magnet and stroke the length of the blade. It is found that stroking the blade many times using the north-seeking end of the magnet will produce a magnetized blade with the north-seeking side of the blade, the one which was initially in proximity or touching the magnet. A magnetized blade's poles are tested by their ability to attract or repel a compass needle. After the blade is cut, it is found that new poles are created in the same orientation as the original magnetic field. If this blade is positioned in a cork floating on water, two pins can be aligned with the blade to indicate the north-south direction. A small pin is magnetized using the magnet stroking process, and this pin can be used to create a makeshift magnetic compass. A piece of cardboard can be suspended from a thread. If the thread ties around a small piece of string securing the thread, the pin can pierce the cardboard twice, such that it is in alignment with the cardboard. Then the pin will point in the direction of the Earth's magnetic pole. Another method of making a small magnetic compass is to cut a steel tin into small strips and then create pivots on which they can balance. The pivots may be made by pieces of cork with pins poking through their center. The steel strips will have small dimples placed in their center, and they are balanced by filing an appropriate amount off one side that is heavier than the other. The steel strips are magnetized using the same rubbing process. An amusing set of magnetic interactions occur when several of these rudimentary magnetic compasses are placed together and are set rotating. They will continue to swing until an eventual equilibrium state is met.
Magnets may be created by the action of other magnets, inducing magnetism within them. Magnets may then be used to detect the presence of a magnetic field from other magnets within the vicinity, or of the largest magnet that we have access to, our Earth.